So this is solubility, chapters 22.4 and 24.3 and 24.4. And it's essentially vocabulary that I expect you to know as we talk about solubility. Solubility is the ability of a substance to dissolve meaning mix together on a molecular level, forming a solution. When I say mix together on a molecular level, what I mean is if I dissolve sugar into water, first of all, I can't see the sugar anymore, but the reason I can't see it is because it's mixed so finely that individual molecules of sugar are scattered amongst the molecules of water. You don't have clumps of sugar, which would be a lot more molecules together, in which case you would be able to see it still. If you can see it, think about it this way, if you can see it, it's not dissolved. If it's dissolved, it's going to be mixed so finely you can't see it. But then the reason for that is because the individual molecules of the substance, or if you're looking at an ionic substance, the ions are no longer together in a large enough quantity that you can see them. And a solution then, when I say solution, I'm talking about a mixture in which the components are mixed on the molecular level. So it is a mixture. This is the kind of mixture where, to quote Hannah Kinzer, you can't see, the components are so finely mixed you can't see them. You can have other mixtures in which you can see the components. And they're still mixtures, they're just not solutions. And that, I believe, is earlier in chapter 22 in your book, if you want to look at the other kinds of mixtures. In a solution, there are two components, or parts, really. There's the solvent, and that is the component in greatest amount in a solution, and there's only one of these. So, for example, in sugar water, water is the solvent. That's the thing that there's the most of. It's the thing that you are dissolving your stuff into. And then there is the solute, and in a solution that's essentially everything that's not the solvent, and there could be more than one. So if I were to dissolve cocoa powder into water, water is my solvent, and then the cocoa powder is my solute. But if you know anything about like cocoa powder, it's actually some cocoa, it's some sugar, it's some powdered milk, so all of those things would be the solute. If you have a solution such as air is also a solution. Don't just think of solutions as being liquids where you're dissolving a solid into a liquid and you get something that's aqueous. You could have a gaseous solution. Then nitrogen is the solvent. That's the thing that there's the most of. Air is 80% nitrogen. And then everything else are the solutes. So the oxygen, the argon, the water vapor, the carbon dioxide, all of that stuff that has dissolved into the air, which is primarily nitrogen. And you may hear the term, some people say water is a universal solvent, meaning most things dissolve into water. In fact, not everything does dissolve into water, but most things do. So when we're talking about solutions, things that can affect solubility, things that can affect how the solutes dissolve, could be the temperature or pressure of the solvent, and that's what's talked about primarily in chapter 24. So some of you know that for a lot of solids, not all solids, but a lot of solids, the hotter your solvent, the greater the solubility, the more that can dissolve. If I have cold water and I'm trying to dissolve my hot cocoa powder in it, it doesn't work as well as if I have warmer water or milk, if that's how you choose to make your hot cocoa. And so the warmer my solute is, in the case of hot cocoa, the more hot cocoa I can dissolve and the more easily it dissolves. Pressure can also change the amount of solute that can dissolve as well. But that said, solubility is, again, like melting point and boiling point, a characteristic property of pure substances, meaning at a given temperature and pressure, in a given amount of solute, a certain amount of pure substance can be dissolved. That's a lot of words, so let me kind of break that down for you. So what that means, like for an example, would be if I had 100 milliliters, which is of course 100 grams of water. Water, remember, has a density of 1 gram per milliliter. X grams of NaCl, sodium chloride, can be dissolved at 50 degrees Celsius. And I don't know off the top of my head what that X grams is, but it would be a certain number of grams in this much water at this degrees. But Y grams of NaCl, sodium chloride, can be dissolved at 70 degrees Celsius. And you can get graphs that give you, at this degrees, this many grams can be dissolved. But you always need to know the temperature and then again, of course, how much solvent you have. That should be a given, that you can dissolve more solute in a larger amount of solvent. If you have a larger cup, you can add more hot cocoa than if you have a smaller cup. And so some of the terms we use to describe how much has been dissolved are as follows. If you have dissolved the maximum amount of solute that you can possibly dissolve, so whatever that X grams is at 50 degrees in 100 grams of water, we would call that saturated. So you say something is saturated when the maximum amount of solute that can be dissolved has been dissolved. And you can actually have a numeric quantity. So, this is saturated when this many X grams has dissolved at a given temperature and pressure. The opposite of that then is simply unsaturated, meaning it's possible to dissolve more solute. So you haven't quite reached the maximum amount yet. And then, in fact, you actually also have supersaturated. We're not really going to talk about that. That is in your book in chapter 22. But similar to supercool, where you have cooled it more than you really should be able to cool it without a phase change occurring, supersaturated is you have added more than the maximum amount of solute that you really should be able to dissolve. And that has to do with changes in temperature and or pressure. Another word we use then is concentrated. So we say something is concentrated when you have large amounts of solute relative to solvent. And again, concentration, you could have a numeric amount of solute in solvent. If you think back to the conductivity lab or the electrolyte lab, depending on what you did. If you measured electrolytes, you were measuring concentration of electrolytes, meaning the amount of electrolytes per liter of solution. So something that was more concentrated had more milligrams of electrolytes per liter of solution than something that was less concentrated. Don't get confused and think that concentrated now means there's more solute than solvent. That's not the case. Concentrated means if you have, for example, 2 solutions, the one that has more solute is the more concentrated one. So let's go back to the hot cocoa example. I have 2 identically sized cups of milk. In one, I dissolve 4 teaspoons of hot cocoa mix, and let's say it doesn't get saturated. So I completely dissolve it. In the other, I only dissolve 2 teaspoons of hot cocoa mix. The one with 4 is called more concentrated than the one with 2. The opposite of concentrated, then, is dilute. You have small amount of solute relative to solvent. So, again, the hot cocoa example, the one with the 4 teaspoons of hot cocoa mix is called concentrated. The one with the 2 teaspoons of hot cocoa mix is called dilute. And especially with dilute, I've heard that dilute is also used a lot as a verb. So you might say, well, this whatever, let's say you're making lemonade. This lemonade is too sweet. I need to dilute it. And so the easiest way to dilute something, obviously it's very difficult to take out solute. The easiest way to dilute something would be to add more solvent. Whereas the easiest way to make something more concentrated would be to add more solute. Because remember, these things, when we're talking about solutions, you can't see the particles. It's not like sand and water, and you want less sand, so you can scoop out the sand. Or you want more sand compared to water, so you could pour out some water. You can't do that with salt water or hot cocoa mix because it's mixed so well you can't see the individual particles. So hopefully all those definitions make sense. If they don't, please make sure you ask tomorrow in class, or if you need more examples or your book's not making sense when you read it, let me know and we will go over those tomorrow.